Now, it's definitely worth considering units when you're dealing with calculus and what different calculus operations will do to your units. For example, we're very familiar with the idea of the slope being the rise over run, but if we have a particular unit attached to our rise and another particular unit attached to our run, then our slope will have units of whatever the vertical units divided by horizontal units might be. So if we have a position time graph and we find the slope of the position time graph, we're finding the rate at which the position is changing with respect to time. If that position is measured in meters and the time is measured in seconds, then the slope is measured in meters per second. And that's exactly what happens when you take the derivative of the position function with respect to time, is you're dividing by a unit of time. And so if you take a second derivative, then you're going to divide by that unit of time a second time. So instead of meters per second, we're going to get meters per second, or meters per second squared. And that's exactly what acceleration is. So differentiating a function means we're going to divide by the units of the independent variable. Okay, so it would make perfect sense if we reverse that process to integration. We would be multiplying instead, right? The opposite is true. So if we take the acceleration function and we integrate it, we're actually multiplying by time instead of dividing by time. So we're going to take meters per second squared, multiply that by seconds, multiply by our unit of time, and one of our factors of seconds cancels out, and we're left with meters per second. And again, if we repeat that process one more time, then the seconds are completely gone, and we're back to meters again. So we normally introduce this concept using motion because it might be the most relatable. You can actually, people are always moving around. But we can also measure rates of change in other units, right? We don't have to be talking about distance per time. We could be talking about volume per time. For example, in this problem right here where it says water is flowing into a storage tank at a rate of W of T equals 3 minus T over 5 gallons per minute. Gallons per minute. Oh, this is a rate, right? This function is giving us a rate. That's very important to focus on. We know that our function is a rate because it says rate here, and because the units are gallons per minute, right? So one thing per something else. That's how fast one thing is changing compared to something else. Okay, so that's analogous to a velocity function. It's not a velocity because it's not distance over time, it's volume over time, but it's analogous. And then it asks us to evaluate the integral and then interpret what it means. Okay, well, let's do the easy part first, kind of the mechanical stuff that we just kind of just do it, right? Like Nike. No, I don't want to break any copyright laws. But if we take the definite integral of this function from 1 to 2, we know how the fundamental theorem of calculus works. We take the antiderivative of our integrand and we evaluate that at 2 and at 1. So when we evaluate that at 2, we get 3 times 2 minus 4 over 10. And then when we evaluate at 1, we get 3 times 1 minus 1 over 10. And we subtract those two things. That's 6 minus 3 is 3, and negative 4/10 plus 1/10 is 5/10, so that's 3.5. Now, keeping in mind that integration means that we're multiplying by the units of time, in this case, the units of our variable of integration. And time is measured in minutes. So we started off with gallons per minute. But we multiplied that by minutes. Our dt is our multiplication part, right? This is the height of a rectangle times the width of that rectangle. So this is a multiplication problem. And we're adding up the area of all of those rectangles. So yeah, we don't normally write it like this, of course, because that simplifies. We're going to simplify that to just be gallons. Okay? So gallons is the unit of our answer. Now, what is this measuring? Is it measuring the number of gallons in the storage tank? If so, at what time? Well, if you think about it, this is an accumulation of area over the time t equals 1 to t equals 2, right? So this means that this is not the number of gallons we have. This is the number of gallons that our volume changed by over the course of this time, right? This is the change in volume. So 3.5 gallons were added to the storage tank from t equals 1. Well, let's include these units. Minute. T equals 1 minute to t equals 2 minutes. So over the course of that minute, from t equals 1 to t equals 2, we gain an extra 3.5 gallons. Okay. So that is a pretty common sort of interpretation. Remember that when we do a definite integral with velocity, we're finding the change in position. So if we do an integration of this, it's going to be the change in volume instead. So again, let those units guide you towards the right answer. Once you figure out what the units are, that's going to really help you interpret what the answer means. So back to velocity again. Let's consider these different integrals. Okay, this is going to be a fairly easy velocity function. It's linear. It goes from 0, 10 to 4, 0 to 8, negative 10. These are different velocities in meters per second at different times measured in seconds. And if we evaluate the integral from 0 to 2 of this function, well, this is going to be, I guess, a 5 and a 10 and a 2. So we're finding the area of that trapezoid. You can do this using actual integration if you want to, but the area formula is pretty easy to use, I think. So we average these guys and get 12.5, and we multiply that by 2, and we get 15. And the units would be meters per second times seconds, or meters. And then if we continue going on and we include not just this trapezoid, but this extra little triangle right here, then we've got a little triangle here of base 2. So the whole triangle, the whole red and blue, is a base of 4 and a height of 10. 1/2 base times height is going to be 20. So we've included some more area under the curve. So our value, our answer has increased. And as we keep on going, we're going to go to t equals 6. So that's going to be right here. But you're going to notice that this little bitty triangle is going to be the same size as this little bitty triangle. But it's underneath the curve, so it's going to be subtracted back away. So we're going to go back down to 15, because that's where we were before we added that little triangle. And then finally, running out of colors, we go all the way to the end, and then this little bit of area right here is the same as the red one over here. So those annihilate each other as well, and we end up with 0 meters. So remember that if we integrate a definite integral of velocity, we're finding the change in position. So that means that this object that's following this velocity function is 15 meters away from its starting point after 2 seconds. It's then 20 meters away from its starting point at 4 seconds. And then it's back to only 15 meters away from its starting point at 6 seconds. So it must have turned around, which I guess we already knew that because we see that the velocity changes from positive to negative here. And then finally at the end, where are we? We're back to where we started, right? We've just kind of turned around and went exactly back to where we started. So so displacement is going to give us this definite integral of the velocity with respect to time. Always gives us displacement. But what if we were asking a different question? What if we wanted to know how far we traveled? Let's say I traveled from home to work, and then from work back to home. My displacement is 0, but my distance traveled is not 0. So what I want to make sure I do here with the distance traveled problems is I want to make sure that regardless of what direction I'm going, whether I'm going in the positive direction or the negative direction, I want to continue to add my distance, right? I don't want my positive distance to cancel out with my negative distance. So what that means is I want to force all of my accumulated distance to be positive. Okay, so that means I'm just going to make the absolute value of v of t my integrand. Okay, and that's going to force everything to be positive. You might recognize that the absolute value of the velocity is the speed, so we could actually write this another way. We can say the integral from a to b of s of t dt. And you might recall towards the beginning of this section we were dealing with absolute value functions. Now we can kind of see some application for why we would care about absolute value functions in integrals.